So let's look at a worked example on these ideas of time dilation and length contraction. So we've got a spacecraft passing a space station with a velocity of 2.6 times 10 to the 8. So that's the relative speed between the two objects. Manufactured length of the spacecraft is 46 metres. And then we've got a question about time. So we've got proper time of 0.3 nanoseconds. That's the time measured in the spacecraft. And we're asked about the observers in the space station. So they're in a different moving reference frame relative to the spacecraft. So their measurement is t dashed. So substitute in the proper time of 0.3 nanoseconds into the formula. Notice that they've kind of simplified. I think it's probably safer to show the substitution before they're squaring it, but then they've kind of cancelled out the times 10 to the 8s. And we get 0.6 nanoseconds from that. Just rub this out so it's not getting in the way. And then we've got the question about what's the length of the space station according to the observers in the spacecraft. So the people on the space station are stationary relative to it. The people manufactured would have been stationary, so that 46 metres is the proper length L. And the observed length for those in the spacecraft, because they're moving relative to it, is calculated as 23 metres. So notice in this example we've got the idea that for the first question we've got something that was measured in the spacecraft. So from their point of view that's t, but the people in the space station, that's t dash for them. Then in the second question we've got the information is about the length of the space station. So that's the L for the people who are in the space station, but the observer this time is in the spacecraft. So they measure L dash. So it's all about L dash, T dash are all about measurements which you take in a reference frame which is moving relative to yours. And L and T are all about measurements which you take in the same frame of reference that you are in.